if I move this at a constant rate here.
Are you supposed to have the apostrophe on the F?
No, because I'm using, this is a different function here, right?
The whole thing.
F is this curve here, right? We're starting with just, so pretend you're starting with some kind of a random curve there, and now you're looking at the integral, which is the area underneath, right? So this is F of whatever here. We had to put F of X. I mean, that's F of X, but we're using a W down here because we're using the X up here.
And on the diagram.
Okay? And in the diagram, it's a T, that's Y. Okay? This is F. Let's just call it F without putting a variable there, because it can be F of whatever variable you want. Okay? The function is that curve. The area underneath is the integral of F, right? So then we have F and we have integral of F. Let's leave off all the, I mean, it's A to some value here, right? We want to think of this as a function, so we're putting an X up there where this thing can move, right? Now what we want to know is, what's the rate of change of this with respect to that variable and how fast I'm moving it? What's the rate that the area is increasing or decreasing? It's just this, right? Because if this function continued and went way over here to a really low point, how fast would the area be increasing then? Not very fast. If it went way up, and then it's going to be increasing really fast. This is just this point. The rate of change of this is this value right here. The rate of change is how high that is. Okay, if you have the area function, the derivative with respect to x of some integral where x is the variable of f of w dw is just f of x. Okay, it's just that. The derivative of the integral of this function f is f. And the thing to realize, it's the upper limit of integration here if that's the variable. That's the thing that's allowed to move here. Okay? The questions themselves that I have in here are pretty straightforward, okay, when we get to them. It's the concept that matters here. And you have to understand that it doesn't, this lower limit, if it's a fixed value, if this is a constant, it doesn't affect it. This affects it. Okay? People wonder, why don't I sub in the other thing? Right? You could do this the long way here. If you have derivative with respect to x of integral a to x, f of w, dw, you could do it one part at a time. You could evaluate this. So you could say this is going to be whatever, if I need to know an antiderivative of that, they tend to use capital F for antiderivative, x minus capital F at a. But now we're wanting to know the derivative with respect to x of that. This part is a constant, so it's 0. This part is not a constant. The derivative of this antiderivative, right? Capital F's an antiderivative of little f. So if we now want to know the derivative of it, it's just little f of x, right? The derivative of the integral of this is just the function itself. Okay? Derivative of the integral of a function is the function. That's what they call it the fundamental theorem of calculus, because it links derivatives, slopes of lines, with integrals, areas underneath curves. Okay? Those two things, if you said, how does the slope of the line relate to the area underneath, it doesn't seem like they really have anything to do with each other, but they do, right? This connects the two of them, which is why they call it fundamental theorem of calculus, because it links those two things.
So what's the formula?
The formula? There's not really a formula for it. The formula is life. This thing right here. Oh, this is a pretty nice formula. If you have I see what you're saying. The derivative of this integral, right? Derivative of integral of that function, it's just, what is that? It's pretty short. F of x. Okay? Well, we actually don't need this page because we can come back to it. You already know area function here, right? The derivative of the integral is just the function itself. Derivative of integral of f is f. What? Oh, because I know, because I made it fancy for you guys to put a box. I photocopied it after I made these. Yep.
Is there like some sort of like an integral of it?
Well, you could do the other way around. We sort of have already done that with the first form of the thing.
Oh.
If we go back there, we had, yeah, we did. Well, we had, yeah, I mean, if we had, well, I don't want to go back into that now, but we had integral of a function, we used an antiderivative. So it's like saying the integral of the derivative. Well, it's like this, right? This is integral of the derivative. For this one, you have to think of this was, we had this capital F prime, that's like integral of f of x, right, itself. The derivative of capital F is just the function itself, right? Does that make sense? A to B. If we're going to use this, if we're going to use a dummy variable here and make the upper limit the variable, okay, this thing. So I'm going to rewrite it down here. I'm going to say a to x of this, but we're going to use some dummy variable here, right? If we do that, this now says the reverse of this. This says the integral of the derivative, right? Integral of derivative. Remember that when we did this before, we said if you have this with a W, if we had this, we figured it out by saying what's an antiderivative of that, right? We needed an antiderivative of that thing. Antiderivative of that thing was capital F, right? Antiderivative, f of x minus f of a. This is equal to this, right? You know that already, okay? When we figured this out before, we said we need an antiderivative. It's just that here we're writing the function as the derivative of the antiderivative, right? Just to see what's happening here. The first one, even though you didn't realize it at the time, said the same thing as what we've said now. Okay, if you write those side by side there, we used it to evaluate things, right? The only difference here is instead of just saying the integral of f of x, I'm saying the integral of the derivative of an antiderivative, so that we can see how this is the fundamental theorem of calculus. This says the integral of the derivative of a function is the function itself, but plus some constant. If you do it that way, this does not cancel out the way it did in the previous one, right? Up here, if you do the derivative part second, this can't. You just end up with f of x, that value right there, right? This thing, this part doesn't disappear because you did the integral second, right? First, if you say the derivative of some function, and then you do the integral of that function, you're left with a constant. When we did the integrals before, we had plus some constant here, right? If you say the integral of from a to x, where a is a constant, of whatever function you want here, x squared, except we got to do t squared here, or w squared, or whatever, right? W squared dw here. You need an antiderivative, right? You could have written this as you could have said 1/3 w cubed derivative of that, right? What's the integral from a to x of the derivative of this function, right? The integral from a to x of the derivative, if this has a derivative in here, this is going to cancel out. You just do 1/3 x cubed minus 1/3 a cubed, right? That's all that is. If this thing is in here.
10 minutes.
That was a short 10 minutes. This this is a constant, right? This can be the plus c part of it here.